All right. Hi, everyone. Today we'll be talking about cryptology. All right. So, what is cryptology? Pretty much it's the study of encoding and decoding secret messages. Encoding is just the process of taking a secret message and making it so that you can't read it. And then decoding is just the reverse of that. It comes from the Greek words kryptos, which means hidden, and graphene, which means writing. And it is the first part of cryptology, which is just the general study of codes. And codes are just a way in order to find out what secret messages are whenever you're decoding and encoding them. And then the other part of cryptology is cryptanalysis, which is deciphering the coded messages without a key, which another word for that is just breaking codes. So some terms here that would be really good for you guys to have throughout. Cipher is just another word for code, which we already explained, just a different method. And a major example of that is the substitution cipher, which just replaces letters in the alphabet with other letters of the alphabet. And that makes it so it's unreadable. And then a key is just that actual thing that you're using, like the type that you're using, such as making A be equal to Z and B equal to Y and so on. It's the actual table that you're using in order to transfer from your secret message to your unreadable message. And then ciphertext is that coded message that is unreadable. And then the plain text is the uncoded message that is just the secret message. So there's two examples here. Hi mother is the plain text that you can understand. And then the ciphertext is that that you wouldn't normally understand without knowing the process of converting it. And that process is enciphering, going from the readable plain text to the unreadable ciphertext. And then decipher is just the reverse process of that.
So I found this image and I really like it to explain the terminology that Tori just explained. So plain text is again the readable format that you can actually read, and then you encrypt it to get the so-called ciphertext, which is the non-readable format, and then you can go vice versa, and so then you would decrypt the ciphertext to get back to the plain text or the readable format.
So back to substitution ciphers, which is just using letters of the alphabet and transversing them. There's two main ciphers that are kind of the opposites of each other. There's monoalphabetic and polyalphabetic ciphers. So the monoalphabetic ciphers is a substitution that's fixed, that doesn't change, and it's used for each letter throughout the entire encryption process. So basically, each letter is mapped to a unique ciphertext letter. So for example, for your plain text, your readable message, every time that there's an A in that message, it's going to be changed to the letter Z. And then every time there's a letter B in that plain text, it's always going to be changed to the letter Y or whatever you end up choosing that to be. And you use that same process all the way through your encryption. And because of that, it's highly susceptible to cracking because it's very easy to notice the pattern that they're doing. As opposed to polyalphabetic, which I'll talk about. And then main examples that we'll be talking about is the @bash, the Caesar, and the affine cipher. For polyalphabetic ciphers, it kind of varies. It depends on which cipher you're using, but it's not stagnant. You don't use the same letter every single time. It's not mapped like the other one. And because of that, most of them are pretty hard to break, and the one-time pad actually is one of the only unbreakable ciphers that we have. And the Vigenère is a really big example, which we'll talk about. And yeah, it's basically you have a chart or something, and you take your plain text and the key, and you map letters to get that, what you need to get that to the ciphertext. So it depends, it varies. It's not always that same letter. So the add bash cipher is one of the monoalphabetic ciphers. And basically you just use this key right here that reverses the letters of the alphabet. So like I was previously explaining, your plain text letter A that you would use is always going to be changed into a Z. B will always be Y, C will always be X, and so on. So for this example, we have throw the key away. T here will always be changed into this G here, because if you can see in the key, T gets turned into G every time. And you just copy that process all the way through until you're done. And so then this plain text is turned into this ciphertext right here.
So I will talk a little bit about some history. So first is Julius Caesar's substitution cipher in 100 BC. So this was used to convey secret messages during their war. The cipher depends highly on the secrecy of the system and not just the encryption key. So Tori talked about the substitution ciphers, mono and poly alphabetic keys. And substitution ciphers can be broken by using frequency of the letters in the language, which is not good, obviously. So I will explain the Caesar cipher a little bit more. All right.
You need to do it?
Yeah.
There you go.
Thanks. Okay, so the Caesar cipher, again, is a monoalphabetic cipher that shifts each letter in the plain text to a certain amount of letters. So as you can see by this image here, the Caesar cipher changes the A to a D. So it just shifts the alphabet over 3. So the key is 3, but say if you wanted to make your own cipher, you could change the shifting or the K to any integer. So Y equals K equals X plus K mod M, where Y is the ciphertext letter, X is the plain text letter, and K is any integer that you want. And M is the number of letters in the alphabet, so 26. So for decryption, if you let X be congruent to Y minus K mod M, and then so, for example, if you have attack at dawn and you have A here as your X, your plain text letter, you can find what cipher text letter it would be. So for Caesar's cipher, he had 3 be his K, and then M, which is your number of letters in the alphabet, which is 26, you would then get D for, or he got D for his ciphertext letter. So that is kind of Caesar's cipher, is he always had KB equal to 3.
All right, so since you guys just saw that mod M, I'm not sure if everyone understands what that is, if they've taken classes that have that. So I just figured we would explain that out. So pretty much modular arithmetic, which is also called clock arithmetic, is the sequence of numbers that start again after reaching a certain quantity. So take a clock, for example. Once you reach 60 seconds, that turns into a minute, and then everything past that will be 1 second, 2 seconds, 3 seconds. You wouldn't say it's 65 seconds. You say it's a minute and 5 seconds. So basically 65 and 5 are equivalent in terms of this modular M, where M would be 60. because that is the quantity that you're sequencing all the way through. So we have a definition for you. A and B are equivalent modulo M if and only if M divides the quantity of A minus B, which is denoted A is equivalent to B modulo M, where A and B are integers and M is the positive integer. So like I said, A and B are equivalent in terms of that M, whatever that quantity that we're getting to, that we have to keep restarting once we get to it. So we have some examples here. 17 is equivalent to 2 modulo 3. Since you get to, so you do 1, 2, 3, and then you get to 4. But because it's modulo 3, we have to go back, and that 4 turns into a 1, and you just keep doing that process all the way through. So 17 and 2 are equivalent in terms of using 3 as our quantity. And you can test that by, since that it's an if and only if statement, you can test that by having the quantity A minus B, which is 17 minus 2, getting you 15. And that M divides A minus B just means that the quantity A minus B is a multiple of M. So 15 is a multiple of our M3 because 3 times 5 is 15. And then our second example, which I thought was really important because we'll be using 26 as our mod for the rest of this, since that we'll be using letters. So 26 and 0 are equivalent modulo 26, since that once you get to 26, and you subtract 0 from that, that still gives you 26, and 26 is a multiple of 26, we all know. So that's why down at the bottom, this chart that we're using, z is equal to 0 and not 26, because once you get to 26, you have to go back to 0. It's just a lot easier. So that's why, and this is the chart that we'll be using from now on, where A is equal to 1, B is equal to 2, and so on. Other sources have A equaling 0 and B equaling 1 and so on. It doesn't really completely matter. This is just the one that we'll be using. And then here is the residue R of A modulo M, which is an integer that is equivalent to A in terms of modulo M. So it's the set of residue R is denoted all integers in terms of M from 1 to M minus 1. And to find this residue R, which is what we used previously with, say, 17 and 2, 2 is that residue R, because 17 is equivalent to 2, and 17 is our A. So in order to find that, if we didn't know what it was, you use this process here. So you take the absolute value of A and divide it by M, and whatever that remainder is, you use that to plug in for these. So if A is greater than 0, then A divided by M gives you that remainder. Then the residue R is just equal to that remainder R. If A is less than 0 and R is not equal to 0, then the residue R is M minus R. And then if A is less than 0 and R is equal to 0, then R residue R is going to be equal to 0. So an example here is, say A is 30. So the absolute value of 30 is 30 divided by our M, which is 26, gives you 1 and 4/26. And so 4 is our remainder. So since that A was positive, that means that our residue R is the same thing as the remainder R, which is 4. And this is just the way that we're explaining it here. This is just plugging it in. And this picture over here just explains further how through the alphabet, once you start at 1 equaling A and all the way through, and Z equals 26, then you hop down to 27 being A, and you just go all the way through until infinity. And then affine cipher, that is our last mono alphabetic cipher that we have. So you just use this right here. Y is congruent to AX plus B modulo M, where A and B are integers that are different. And you just plug in whatever it is. And X is going to be our plain text letter that we're using to try and convert it. And Y is the ciphertext letter, like we said before. So here's an example to help you guys out. The plain text, do not drink it, using the algorithm y is congruent to 3x plus 4 modulo 26. So our x would be d if we're starting at the beginning. So d is congruent to 4 using this table. You plug that into the equation. 3 times 4 plus 4 is 16. And then you go back to our chart and see what 16 is, and it looks like that's P. So that P is now going to be our new ciphertext letter. And O is it gets a little bit tricky. So you have O being equal to 15 on this chart. Plug that in. 3 times 15 plus 4 is 49. Now, like we said before, since it's not in the first row, in the first modular of 26, we have to go past that. So we use that equation that we had before, take the absolute value of 49 and divide it by m, which is 26, and that gives you 23 as our remainder, and that gives you w. And you just repeat this process all the way through and obviously once I got to N and then O, we just did O, so I didn't repeat it. But these are just the process. It's the same thing. And then once you're done, you get all of those letters that you had at the very end. That becomes your ciphertext. And you put them in the same order that they were. And there you have it. And you don't have to have them in that same spacing. How do is 2 letters. So at the bottom I have PW as 2 letters. You don't have to do that. You can put them all together so that it makes it more difficult to read. But just for the sake of it, seeing the symmetry to it, I figured I'd just leave it like that.
So I will talk a little bit more about some more history. So Blaise de Vigenère, this is him. He created the Vigenère cipher. So it is a polyalphabetic cipher. He made it in the 16th century. He was a Frenchman, obviously. Blaise de Vigenère, it's really French. It is a series of interwoven Caesar ciphers, and it uses a keyword which controls letter substitution depending on which letter of the keyword is used. So I will talk more about his cipher in this next slide. So you can see this table right here. This is the Vigenère key, as you would say it. It's a polyalphabetic substitution cipher that repeats a single keyword for the length of the secret message. So, for example, let's just say our keyword is run, and we want our plain text to be the eagle flies at midnight. So, to encrypt our plain text, we pair each of the first letters, then the second, third, so on, so forth, etc. And then we use this table here, Vigenère's table, and connect each pair of the letters to find the ciphertext letter. So you could go either way. You could go horizontal first or vertical. It doesn't matter. So R, you could say, so I'm going to go horizontal. So go to R, and then you also go down to T, and you find it to be K. So you do this for your whole string, and you get your ciphertext, which is K, B, R, V, UTs, and so on and so forth. So that is Vigenère's cipher. And then I will also talk about a polyalphabetic cipher machine. So Enigma is this machine, as you can see. It was created by German engineer Arthur Scherbis at the end of World War I in 1918. It was also heavily used by the Germans in World War II as well. It is an electromechanical machine made of several shiftable rotors. As you can see in the picture, there's 3 rotors there, and it converts each letter typed on the keyboard. Enigma was also used for just military purposes. It was just used for military purposes only. And then, however, post war, a lot of businesses were trying to secure their data. And so they were very attracted to cryptography.
All right, so we went over monoalphabetic and polyalphabetic substitution ciphers. This is the third one, polygraphic substitution ciphers. And that basically takes plain text letters and puts them into groups of letters, and then doing the encryption and going through that to make them into ciphertext letters that way, instead of doing it one by one, like how the mono and the polyalphabetic substitution ciphers did. And the major example is the Hill cipher, which we will get into. So basically with the Hill N cipher encryption, you just take an invertible, which is very important, it has to be invertible, N by N matrix key that are integer elements, and you end up multiplying that by your plain text letters that are converted into numbers from that chart that we have, where A is 1 and B is 2 and so forth. So in order to do that, you first choose your key, or it's given to you. Then number 2, you put these plain text into n groups of letters. Now the n depends on how long this plain text is. If it's a really long sentence, then you should probably do more grouping each plain text into 3 or 4 groups of letters. If it's a smaller sentence or even just a phrase or two, I would definitely recommend grouping them into 2 pairs at a time. So say the word hello, you would group it HE together into, if you're doing 2 pairs, and then LL. And then for that O, it's kind of left by itself, but you can't do that because we'll be multiplying these. And you can't multiply a 2 by 2 by a 1 by 1. You can't do that way. So you need to have it give you another arbitrary variable. So you could either just choose X, since that's just what most people use, or you could repeat whatever that letter was. So for us, we have O, just add on another O. It really doesn't matter. It's up to you. They'll understand at the end. But then you take those groupings and you convert them into column vectors. And then, so your HE, whatever numbers they end up being, H I think is 8, E is 5, and so on. And then you take your matrix and multiply that by each of the column vectors. And then once you multiply it, you get different numbers. And remember to convert them into modular 26 so that they end up being alphabetical numbers. And then transfer those back into alphabet letters. And then that becomes your ciphertext. So since that sounded like a lot, here's an example. So we chose a 2 cipher because that's just easier to do than other ones, just for the start out, So we let A, our key, be 2113, and yes, it's invertible. We had to go through and check that. And we'll be using this chart like we have been. So 2, our plain text is hide now. So we grouped that into HIDENO, and then W, you could add an X to it, or you could add another W. For us, we added another W. And then 3, you turn those into those corresponding numbers. H is 8, I is 9, D is 4, E is 5, and so on. And then the 8, 9 becomes its own vector, column vector, as you can see down here. And you do that for all of them, become vectors. And then you multiply that A by each of them. And then do modulo 26. So here, once we did the multiplication, we got 25, 35. And 35 divided by 26 gives you some odd number, I think. Oh yeah, 9. It ends up giving you 9 because then you look back up over here and it gives you I for 9. So that's how we got our I. Same thing for 1319. We didn't have to do that because that's already numbers within the 26. 43, divide that by 26, and that ends up giving you 9, or not 9, I'm sorry, whatever Q ends up being, which is 17. 17 modulo 26. And then same thing for 59 gives you G, 69, and then 92 for Q and N. Then you pair all these back up in that same order, and this ends up giving you your ciphertext. Okay. Now we're going to talk a little bit more about modulo M in order to then find the decryption of the Hill ciphers. So you got a definition here. A number A in the integers of M has a reciprocal modulo M of A inverse in the integers of M if A times that A inverse equals the inverse of A times A, which equals 1 modulo M. And to know that you're getting a reciprocal that works, you have to make sure that M and A do not share common prime factors, which I'm sure you know what that means. But for example, M and A, for M being 26, that means that A cannot be divisible by 2 or 13. And then number 2, in order to find this inverse or this reciprocal X, you would take A times some X that would give you 1 modulo M. So, and then your A inverse would give you that X modulo M. It's in that format. So for an example, 3 has a reciprocal modulo 26, since that it's not divisible by 2 or 13. And then 3 times 9 is our X, gives you 27, which is equivalent to 1 modulo 26. So that would mean that 3 inverse equals 9 modulo 26. Another example is 6. You cannot have a reciprocal for 6 because 6 is divisible by 2. If you're doing modulo 26, of course. Okay, finding an inverse for A modulo M for 2 by 2 matrices. So let A, B, C, and D be integers, and we're going to have it in modulo 26. Then the inverse is just like how we normally would find the inverse for 2 by 2, except for you're not allowed to use fractions. You're not allowed to have like 1/3 out here. It has to be 3 inverse. And then you have to do that process that we just did in order to find what that inverse is. But most of the time it ends up, this is the list of ones that we have here. So it doesn't go all the way out, but these are definitely ones that we'll end up using. So you can just use this chart because it's a lot easier than trying to come up with what those numbers are. But yeah. And of course, you can only have those numbers if they are divisible by M, or divisible by the same ones that M is divisible by. So for 3 by 3 matrices, in order to find the inverse, you can't use that process, as we know. So we do the one that we normally would do, which is the augmented matrix of A and I, reduce row echelon form that and get I, the identity matrix, and then A inverse. However, you can't go through the process with dividing out like how we normally would. So you have to use these 2 steps here in order to either make these numbers into zeros or make them into ones. So I wrote up a little example of a 3 by 3 matrix that we need to invert. So for example, take this 9 that we want to become a 1. Instead of dividing by 9, which we can't do, we would multiply by its inverse in order to get 1. So from that chart that we have here, 9 times 3 gives you 26 or 27, which ends up giving you 1 modulo 27. And I have it written out here, just a little scratch work. And then if you're wanting to take this 5 and turn it into a 0, you just have to make it equal to 26, because we know 26 is equivalent to 0 modulo 26. So, but a key thing in order to do this is you have to make sure that there's a 1 in that same column that you're trying to convert it, because otherwise it makes it a lot more difficult. So for here, we have a 1 above it. So we can do 21 times R2, row 2, which is 1, plus R3 of 5 to give you 26, which turns it into a 0. But as we know, we have to do that through the entire row. And so I have that written over here, just as the other ones that we would have to do, such as 3. And then the rest of these are just more examples of how to do that same process. But yes, generally, if you're wanting to make a number turn into 0, you have to get it to equal 26 by multiplying it by some other row that has 1 in it and adding that number. And then if you're wanting to get that number to equal a 1, you have to get it to equal that 27 or 52 or 78 or whatever that ends up being, that will reduce to 1 modulo 26, which by doing that, just simply multiply by its inverse. All right. So now that we have that information, we're able to do the Hill cipher decryption procedure. And it's pretty much the exact same opposite reverse of doing the encryption, except for you have to use the inverse of that matrix in order to multiply through and get your ciphertext. So 1, you find that inverse, which is that same process that we did just before, either using the 2x2, 3x3, and so on and so forth. Then you convert your ciphertext into n groups of letters, and those ends have to be the exact same, otherwise you're not able to multiply it through, and put them into groups, and then convert those into your numbers, and place those into column vectors, and then multiply that inverse by each of those column vectors, and then each of those answers, those products, will give you your ciphertext that you have to convert back into alphabetical letters. And yeah, you can ungroup them, like how I said before. You don't have to leave them in the same spaces, in the same groupings that I have at the very beginning. You can shove them all together to make it even more difficult. So a good example, I just use the exact same process for the end cipher, but just the reverse, just to show like how it looks. So A is still 2 1 1 3, and I went through, and since there's a 2x2, I was able to use that algorithm that we had. So AD minus BC is 2 times 3 minus 1 times 1, which gives you 5 inverse. And from that chart that we have, we know that the inverse of 5 is 21. Multiply that by plugging in each of the AD, negative B, negative CA, and then convert this into modulo 26. And remember, in order to get your residue R, if it's negative, you have to take the absolute value of A, say for 21, negative 21, you take the absolute value of negative 21, which is 21, divided by M, which is 26, and that gives you 21 over 26. So your R remainder is 21, but since the A is less than 0, you have to take M minus the remainder R, which is 26 minus 21, which gives you that 5. So that's how we got that. The other ones are just basically how we've done it before, because A is positive, so we already know that. But just remember, if it's negative, you have to do that process, because otherwise the numbers won't make sense. But yeah, so then after you have that, then you multiply it by each of the ciphertext letter groupings that you have. And remember, we grouped them into pairs of 2 since it's a 2x2 matrix, and multiply those through. And then once you get that big number, then remember you have to convert those into modulo 26. So 320 is equal to 8 modulo 26. And that 8 becomes our H. And the 9 becomes our I, and so on and so forth. And that gives you hide now.
Okay, so next I will talk about more history of cryptography and different types. First records of cryptography were Egyptians and how they used hieroglyphics to send messages ordered by kings. So the idea of concealing secret messages has been around for thousands of years, but really, science behind cryptography started about 100 years ago. So, transposition ciphers were the first actual type of cryptography, followed by substitution, which we talked about. So the rearrangement, transposition is the rearrangement of letters in a message. For example, hello world becomes that. And I will talk about two different types. So first, we'll talk about rail fence. So rail fence is a transposition type of cryptography. As you can see in this image, we have a plain text of this is a secret message, and our key is 4. That's just what it is for rail fence. And so instead of going straight across horizontally, you just go diagonal and downward writing instead of straight across. So if you didn't know to go diagonal and downward, you would just think the message is this ciphertext of TATGH blah blah blah, and you wouldn't know what the message is. So that is what rail fence is. And
Do you want to do it or do you want me to?
no, you can. You can. It's okay.
Okay, well, this is just another example of a transposition cipher. Like Molly said, it's just rearranging them in different ways, but not actually changing the letters themselves. So column, you just use matrices. So for our plain text, we have golden statue is in 11th cave, and it is written in row form from top to bottom, as you can see. But then in order to make it into a ciphertext, you just take it and write it out from column wise, from left to right instead of row wise. So then that gives you your G and then N and then U, N, E, A, O, S, and so on. And like Molly said, then if you didn't know which way to go in this column, whether rows or whatever, they wouldn't, or if they just gave you this GNUN over here, this just thing, but they didn't know that you're supposed to put it into a matrix, then there's no way that they would know how to change it. But if they do know, then if the reader and sender do know how to do it, all they need is the number of columns in order to place them in the correct places. And that's how you do that one.
So next is another transposition cipher. It's called Sitali. So Egyptians and ancient Greeks used this. As you can see, it's very old. So it's just like a piece of paper wrapped around a cylinder, like ribbon like. So you would take your paper, you would wrap it around a cylinder, you would write your message on it, and then you would get this piece of paper where you can't really see what anyone is saying. So this is very old, and the bad thing is when your sender and receiver, they must have the same diameter rod in order to see what it says. So this was very old, very interesting. So yeah. And some modern ciphers, we have block and stream ciphers, which were made in 1950s based on another cipher called just product cipher. It is the combining of simple substitutions, which we talked about. And there's two types. So there's symmetric key cryptography and there's asymmetric or public key cryptography. So symmetric means both the sender and the receiver share the same key for encryption and decrypting a message. So I have an image to help explain that. So the symmetric key, like I explained, it has one key. So to encrypt your message, you use that same key, and to decrypt your message, you use that exact same key, which is more easier to break. But next I have the public or asymmetric key cryptography. So this is also more modern in 1976 by Whitfield Diffie and Martin Hellman. So in public key cryptography, there's two different keys that are used. So there's a public key and a private key. So calculation of the private key is computationally unacceptable from knowing the public key. So it's a lot harder to break. So David Kahn, which is a historian, said public key cryptography is the most revolutionary new concept since polyalphabetic substitution. And I have another image for you guys just to help you like learn it. So as you can see, there's two keys. So to encrypt a message, you use the public key, and then to decrypt a message, you use a completely different key. So that's also a lot harder to break than the symmetric key. So yeah.
And then this is breaking ciphers. So of course, if you have how she had the public key, it's very difficult to break. So it's pretty much unbreakable as well as that one-time pad. But monoalphabetic ciphers, very easy to break because you just rearrange the letters and you use those different types of keys, either going from A to Z and flipping it, so AZ, or which was the @bash, or doing the Caesar cipher where you just bump that letter over a few different times to get it to be that new ciphertext, or with the affine, just figuring out what numbers go in that AX plus B format. It's pretty easy, and there's other ciphers like that, but generally monoalphabetic ciphers are incredibly easy to break. So like even new beginners could probably figure it out. Like with that, at the very, very beginning of our presentation, we had what was it? Hi, mother. I'm sure before I even explained that it was backwards, you guys could have figured that out. With polyalphabetic ciphers, they're a lot more difficult, but of course not as difficult as Molly was saying with the public. But some were broken, like the Visionaire cipher. It was at one point the unbreakable cipher, but of course with time it got broken, and they figured out that chart, and then of course we couldn't really use that anymore. And then that actually got turned into the one-time pad, which is one-time pad we haven't completely discussed. It's pretty much taking a key, which is the length of the message itself. It's kind of like the Visionaire where you take and it's a giant pad, but it's the entire message, and it could be like a paragraph long of the secret message, and every single letter is completely different. And so that one is actually the unbreakable, one of the only unbreakable ciphers that we have. And there's a few ways to break it, by one, just using your own common sense and arithmetic and stuff like that to figure it out. One example though is the frequency analysis, and that takes, just by looking at whatever word you're using, and guessing what each letter ends up being, depending on the amount of letters that are the same throughout that encryption. So for example, E, the letter E is the most number of times that it's going to be there. E is very frequent in messages and other vowels. Most vowels are very frequent because you use them a lot. So if you're even just in this slide right here, guess letters by number of times they appear, E is in most of these words here. If not, yeah, almost all of these words have the letter E, and most of them have the letter A. So if you just look at a ciphertext like that and just see, oh, there's a bunch of X's, then X is probably the letter E, and just doing it that way. And there's other ways, but that's a very common one. And then we have over here just a big example, which we got from the textbook, of breaking a Hill cipher, given part of the code that you already know. But this one is pretty interesting. So say you're given this ciphertext up here, and you heard or somehow figured out that the first 4 letters is the word deer. So you take that deer, convert those into our numbers, where A is 1 and D is 4, E is 5, R is 18, and then compare those with your first 4 letters of the ciphertext, I, O, S, and B. And just compare those and figure out a way to create the inverse matrix. So put these first into this matrix, and then take your IOSB and convert that into the numbers. And so we're going to let C be equal to those numbers in that order, 9, 15, 19, 2. And then to find the key that you need in order to decipher it, you take the augmented matrix C and then P, which C is the IOSB, P is the deer, and then reduce row echelon form it, modulo 26, like how I showed you guys, and get it down to the identity matrix and then the inverse of A transpose. So for this one, for this example, you have C and then P right here, C and then P, reduced row echelon form it in terms of modulo 26, since we're using letters. And then here you have the identity matrix after you're done reduced row echelon forming it. And then this here is 1, 0, 17, 9 is now your inverse of A transpose. And we want the inverse because we're deciphering it. So all you do is you just do the transpose, and we know how to do that. And then the next 4 steps are just how I explained with the deciphering of Hill ciphers. You take that and you multiply it by each 2 grouping of these once you convert this into numbers. So IO, SB, TG, XE, SP, XH, OP, and DE. Convert those into numbers, multiply those through, and then convert whatever that is, modulo 26, back into your letters. And after doing that process, which I didn't put up here because I figured we already explained it and you guys know how to do it by now, right? And the plain text is Dear Ike, send tanks. So it's really interesting that you're able to figure out things just by using a few letters from the entire ciphertext. So yeah. All right.
So we have a homework problem for you guys. So we intercepted an encrypted message that Jared sent to Dr. Schaefer. We know it's a Hill 3 cipher. So we explained Hill 2 cipher, but to spice things up, we're going to give you a Hill 3 cipher. But it's basically the same process. So just go through again in our slides, or the slides that Tori explained in the Hill cipher. And so we are giving you the cipher text, and we need you to crypt or decrypt this message and find the plain text. So there you go.
And we already took the liberty of making sure that this 3x3 key matrix is invertible. But yeah, you'll have to actually do the inverse of it, like how we did in our steps, and then go through that process. And also, little hint, guys, we put it in this form with these odd spacings so that you know how to space them out when you're done with the plain text. So yeah, let's figure out why Jared didn't show his face on Zoom throughout the whole semester. And what we talked through with Jared, make sure it's all right to bring him into this. Not sure Schaefer, we talked to her about it, but I think you guys will enjoy it.
It's fun.
All right. Well, I hope you guys enjoyed this presentation. And I hope you guys learned as much as we did from going through it and studying all this much. But yeah.
All right. Well, good luck.
Yeah, good luck. It shouldn't be too hard, but all right. Bye, guys.
Bye.